All right, fundamental theorem of calculus part 2 is the practical one. Part 1 is the heavy lifting, part 2 is the practical application. What does the fundamental theorem part 2 say? It says the definite integral of f of x dx is simply the antiderivative evaluated at the upper and lower endpoints and looking at that difference. Riemann sums would be a real pain in the neck and not all that practical if we had to do them all with the limit definition of the Riemann sum. Like that one question I did that took me a whole page. But the beauty is, once you got the fundamental theorem of calculus, you can do those Riemann sums just like that using the first half of calculus. All right, here's the proof of that. Okay. So consider integral from a to b of f of x dx. So this is, I think it's on page 2. The integral from a to b of f of x dx. Okay, let's let capital F of x be an antiderivative of little f. We know at least one exists. At least one exists by the fundamental theorem of calculus, part 1. Why? Yeah, well, we need f to be continuous. Yes, maybe I should have said this. I should have said that, f is continuous. So I know there's a function g of x equal to a to x of f of t dt. What's the derivative of this function? Well, we could label it as g prime of x, but what is it? It's the underlying function f of x, right? So if the derivative of g is f of x, if these two are equivalent, then what's an antiderivative of f? And yeah, but we don't know what that is. An antiderivative of f would be the same thing as an antiderivative of g prime, and what is the antiderivative of g prime? G. So that is one antiderivative of f. So we know at least one antiderivative of f exists. Then so we have this other antiderivative that we've chosen. What do we know about it? What do we know about two different antiderivatives of the same function? They can only differ by a constant, right? So what do we know about f of x? Even though we don't know how it's written, we know that it's equivalent to this thing right here, plus c. Now, I'm not saying that f of x is going to look like that, but it will be equivalent to this. It will always return the same values as this expression does. Usually, when I say think of an antiderivative of f, you will not think of this function, but this function is an antiderivative of f. But usually when you go to think of one, you don't pick this one because this one's so messy to work with. But it is an antiderivative. Okay? So here we go, we're done. So f of b minus f of a is equal to the integral from a to b of f of t dt plus c, right? Because we said, what did we say capital F of x was? We said capital F of x is just that function, and so if I put a b here, then I put a b here, right? Minus, what is capital F of a? It would be the integral from a to, I'm doing this one right here, it would be the integral from a to a of f of t dt plus c. What happens to those two plus c's? Cancel, which is why we've never had to worry about the plus c when we use the fundamental theorem part 2 for definite integrals. Okay. So what am I left with? Well, I'm left with the integral from a to b of f of t dt minus the integral from a to a of f of t dt. But what is the integral from a to a?
0.
It's 0. So what am I left with? The integral from a to b of f of t dt. Why was t there all along? It was a dummy variable holding the place of whom? X. What did we just show? We just showed that the difference between these two antiderivatives, evaluate the endpoints, is the net area underneath the curve.